Next topic that we're going to talk about is monitoring machine learning models. So once you've deployed the model, how do you make sure it stays healthy when it's deployed? There's a lot of things that can go wrong with your model once you've trained it. For example, maybe the model that you trained wasn't good at all, like validation loss wasn't actually below your target performance, or maybe your test losses was actually worse than your validation because you overfit your validation. But as you start to get more into the process of building your model, you'll get to the point where you have a model that performs well, not only on your validation set, but also on all of the critical slices and metrics that you really care about. You'll have looked at the predictions qualitatively and they'll make sense. You'll have verified that the production model and the original model that you trained have the same performance characteristics, so there's no like changes in the production model that cause the performance to degrade. And you'll have maybe even run an A/B test and verified that the production model is indeed actually better than the model that it's replacing. We covered some of this in the training and troubleshooting lecture a couple weeks ago, and we covered the rest of it in the testing lecture last week. So you're done, right? Nothing else can go wrong with the model. You can just deploy it and forget about it. Not quite. So an unfortunate fact about machine learning systems is that model performance tends to degrade after you've deployed the model. And so one way to kind of reason about this is if you think about what are your guarantees, or what is the problem that you're solving when you train like a supervised machine learning model. So you're approximating some like P of y given x, and you're doing that by learning a parameterized function on data sampled from the joint distribution of x and y. And theoretically, what are the things that can go wrong? One of the things that can go wrong is that P of x can change. So the distribution of inputs into your model, that probability distribution can change. And you'll see this referred to as data drift. Some examples of this are, let's say that you depend on some feature that's being created by somewhere else in your pipeline, maybe even by some other team. That team changes the way that they define that feature, and potentially they even introduce a bug where all of a sudden all the values of that feature are like -1 or something. So that's one way that P of x can change. But it's not only bugs. So malicious users can also change P of x. They can give you intentionally weird inputs. You could, for example, launch your service in a new region, and that might change the distribution of inputs. Or you could start onboarding new users, and those users might have different demographics than the users that were present at training time. Another thing that can go wrong is that P of y given x can change. And so you'll see this referred to as model drift or concept drift in the literature. One kind of concrete example of this is like maybe your user's behavior changes, like potentially even in response to your model. So for example, if you're building a recommender system and you make some recommendations to your users, their preferences are going to change after that because they might actually like click on one of those recommendations and watch that movie. And then that might change the types of movies that they want to see in the future. And then the last category of things that can go wrong is that we're approximating this parameterized model. We're approximating this probability function using data, a parameterized model that's trained on data that's sampled from the underlying distribution. And so there can be artifacts that are introduced by the sampling process itself. And so some names for this are like domain shift, where there's like some difference in the domain between training distribution and target distribution. Or another term that describes this is the long tail. So if your data distribution has long tails, then randomly sampling that data might not give you all like data points that represent all the parts of the distribution that you care about. So some examples are tasks where outliers really matter. So if there's something in the probability distribution that only happens 1 out of a million times, but if you get the prediction wrong, that's really bad. That's an example of where you might not have adequately sampled the distribution. Bugs in the training data pipeline can cause this. And this is often also very frequently caused by bias in the sampling process. So let's talk about different types of data drift. So if this is like the time series of our data points, like the value of that data point is on the y-axis and time is on the x-axis, then there's a few different types of changes that this data distribution can take that are worth being aware of at a high level. So one is instantaneous drift, and you'll also see this called distribution shift. So where like all of a sudden the distribution changes. Some examples of this are you deploy your model for the first time in a new domain, like maybe you deploy your self-driving car in a new city, or bugs getting introduced in the pre-processing pipeline can cause this type of shift. But also like big external events like COVID happening can cause this type of shift as well. Something happens, all of a sudden the world is different, the data that comes from the world is different as well. You could also have gradual drift, so the distribution, like the values of the feature change gradually over time. For example, like users' preferences might change over time as a result of like your users getting older or like pop culture changing around them, or like new concepts can get introduced to your corpus over time as well. You can also have periodic drifts, look like these directional drifts, but then they change directions and repeat over and over again. So, some types of user preferences might be seasonal, or for example, maybe like people in different time zones use your model differently, potentially, let's say, because they speak different languages. And then the last category of drift that we'll talk about, and the probably the most difficult one to actually detect, is temporary drift, where like all of a sudden there's a big change in the data distribution, but then it goes back to normal. So, for example, maybe this change in your distribution is a malicious user attacking your model, or it could be like, let's say some new user tries your model, their data doesn't really look like the data the model is trained on, so they get bad results and they churn. That could also produce a drift like this. Or just someone using your product for the first time in a way that is not intended to be used. So these are the different ways that data drift can manifest themselves in your production machine learning system. And one question you might ask is, okay, I get why this is a theoretical problem, but is this actually a real problem that affects real world machine learning systems? And the answer is that this can actually have a huge impact in production. There's this article from, can't remember the publication, I think it was maybe like Forbes or something, that was like describing what was happening with all the machine learning models during the pandemic, because all of a sudden like everyone's models drifted. And so some really weird stuff started to happen. Another story that I heard from someone who was building a machine learning system at a kind of e-commerce type company is that they had a bug in their retraining pipeline that caused them to make the same recommendations for their users over and over again. And so that the new users that came in particular were like just saying, oh, this service is just telling me to do the same thing over and over again. This is not useful. Most of them churned, and they estimated that it took them a month or a couple of months to catch this, and they lost like millions of dollars in revenue as a result of this bug. So this is a real problem that affects like a lot of companies, and I think is only just now starting to get like the attention paid to it that really needs to be if you want to build reliable machine learning systems. Most of the rest of the lecture will talk about different strategies that you can use to detect these types of changes that might affect your model. Quick outline. First, we'll talk about what you should be monitoring. Then we'll talk about like how you measure if that thing is actually changed. Then we'll talk about how you can tell if that change is a bad change or not. Then we'll talk about tools. And then finally, we'll talk about like where monitoring fits into the broader context of your machine learning system. Firstly, what should you monitor? I think there's 4 signals that you should probably consider monitoring that trade off with each other in terms of like how useful they are if you have them and how hard it is to get them. So the most informative thing to monitor about in order to tell whether your model's performance is changing is to look directly at the performance of the model. And so this is the easiest thing to do. There's still some technical challenges associated with it, even if you have labels. But this is the hardest of all these to do because for many of the problems that we're working on, machine learning models are difficult to get labels for, especially in a timely fashion and in a cost-effective fashion. So if you don't have access to like infinite free labeled data that comes in right away as soon as your model makes the prediction, then what are the other signals that you can look at? So another really informative signal to look at is business metrics. So if you're building a model I'll come back to the recommendation example, there's some metrics that you might really care about that driving, like user engagement or user click-through rate or things like that don't actually tell you how accurate the model is because there's some conflating factors that also help determine those business metrics. And so that's why it's not like quite as useful a signal in terms of like really telling whether something went wrong with your model, because there's other things that can cause those signals to go awry as well in many cases. On the other hand, they're often easier to measure because you often have access to these signals already. You're already measuring these things as part of your like analytics team. Another signal that is worth looking at is the inputs to the model and the predictions that are coming out of the model and the distributions of those inputs and predictions. This is also can be quite informative. Like you can detect drifts this way just by looking at the raw data, even if you don't know what the label should be. But there's still a bit of an art to how you actually measure things when you're looking at them at this level. And we'll talk a little bit more about why it's such an art. But this is also something that's worth doing if you have limited access to like labels and business metrics. And then finally, the baseline thing to do is just monitor system performance. What is your GPU utilization? What is the average latency of your requests and things like that? And so this will only catch like very coarse bugs, like your servers crashing or something like that, or memory leak maybe. It's really important to measure, and it's very easy to measure because there's really good tools for doing it already. But it doesn't really tell you about the more machine learning specific stuff like your model performance. Different ways of like categorizing these things. that like some terms that I'll use. Model metrics, and in some cases business metrics, are what I would call like ground truth performance metrics. So these are things that like actually tell you directly how well your model is performing. Model inputs and predictions, as well as business metric, as well as like some other business metrics that are like have more confounding factors, or what I would call like approximate performance metrics. And so these are ways of, if you don't have ground truth performance metrics, ways of approximating how well you think your model should be performing on the data that it's seeing before you have access to labels as to how well the model is actually doing. And then lastly, system performance and some types of like model inputs and predictions, or what I would call like system health metrics, which are helpful for telling if your system is working as intended, but aren't really helpful for telling you whether your model is working as intended. So those are the signals that you might want to measure. Okay, so we talked about the different signals that you can look at. The next thing that we're going to cover is like, how do you actually measure if there's been change to those signals? So the overall strategy here for measuring distribution change is we're going to select a window of data that we consider good, like this is what the data should look like, to serve as a reference. So in this example, this is the reference on the left. How do you pick this reference? How do you pick the data points that you consider good? One way you can do it is you can just pick a fixed window of production data that you believe to be healthy. Some papers that you'll see will advocate for using a sliding window. So like always using a window of data that's 1 day behind or 10 hours behind or whatever the window that you're actually trying to tell whether it's healthy. But I think the pragmatic thing to do here is most of the time you should probably just use your training or evaluation data as the reference, because that's ultimately like what the model was trained and evaluated on. And so if data that's coming in production looks different from that, it doesn't really matter if it isn't too different than the data that you saw in production a day ago. It's still different from the data that you really care about, which is the training data. Next thing that you'll do is once you have this reference window of data, you'll select your new window of data to measure a distance on. How do you select that measurement window? Very problem dependent. I'm not aware, at least, of a principled approach for saying, okay, should I monitor like an hour of data or a day of data or like a minute of data? I think pragmatically, one thing that you can do is just pick one window size or a few window sizes and just slide them over the data. So every day monitor on the last day, every hour monitor on the last hour, something like that. There's a special case here, which is like where your window size is 1. And there's a whole separate class of techniques here called outlier detection, which is, I think, present in some like model monitoring libraries, less practical for a number of reasons, but it's worth being aware of as well. A couple of footnotes here if you want to dive more into this stuff. And so the last thing that we'll do is we have our like reference distribution and the distribution we want to measure, and we'll compare these two windows using some distance metric. So what distance metric should we use? First, let's consider the case where the data is like continuous and one-dimensional. So there's a couple categories here. One is rule-based metrics. You'll also see this referred to as like data quality metrics. And then there's statistical distance metrics. And so these are things like KL divergence, your KS statistic, something called a distance, and like plenty of others. So let's talk about rule-based distance metrics or data quality metrics. So the kinds of things that you'll measure here are like, okay, for this window of data is like the minimum value and the maximum value and the mean value within some acceptable range that's determined by the reference window, maybe plus some allowable excess beyond that. You might also check like, are there enough data points in this window? Or are there too many missing values in this window? Is there a bunch of NAND out data in this window? You can also measure more complex things like, are all of the values in this column bigger than all the values in this other column? And there's a whole host of other different like kind of rule-based metrics that you can use. There's an open source library for this that is gaining a lot of popularity recently called Great Expectations, which helps you like define these tests. It's not machine learning specific, not like super well suited out of the box to being used for like continuously streaming data, but it's works pretty nicely for like batches of data. So you might need to set up a little bit of infrastructure on your own, but then you could run these tests on that data when you do that. Recommendation here is this is very much worth doing. There's two, I would say, like landmark kind of industry standard papers on monitoring machine learning models, which I'll link to at some point later in these slides. One is from Google that describes their TFX system, which is, they have an open source version of it, but it also is a thing that they use internally. And then the other is from Amazon, which is also used internally and is also part of an open source library called DQ. And what both of those papers concluded was that like these rule-based metrics for detecting changes in data distributions are much easier to use than the statistical metrics that we'll talk about later, and already catch like a huge percentage of bugs. And like the pragmatic thing to do is just use these rule-based things and like maybe try layering on some statistical stuff as well. But you'll be in good company if you use this as a starting point. All right, next let's talk about some statistical distance measures. And so we'll start with every machine learning person's favorite statistical distance measure, the KL divergence. This is KL divergence. It's an expectation of a ratio of logs between the two different distributions. It's not actually a distance metric, it's not symmetric, and it's a very bad distance metric for detecting data distribution shifts. There's a few reasons for that. One is it's really sensitive to what happens in the tails of the distribution. So for example, since you're looking at a ratio, like a log of the ratio of probability values, if you have in some tail of the distribution for one of the probability distributions, you have a value of 10 to the negative 4, and in the other you have a value of 10 to the negative 3, then that ratio is going to be 10, which is going to be a really big contribution to your KL divergence when you take the log of it. So it's like mathematically not really the right thing when you're sampling your data, and so like the tails are going to be pretty noisy. It's not very interpretable, so it's like not super clear how you explain to someone on a chart what this distribution distance is measuring. And it's not very clear what to do if P and Q contain data that doesn't fall in exactly the same range. So you're gonna end up with a zero, like a zero in a log or a zero in a denominator somewhere. And so that's another reason why this is tricky to use. So recommendation here, don't do it. Don't monitor the KL. It's very tempting because it's a familiar distance metric in machine learning, but there's better things to monitor for this particular use case. And yeah, I posted about this on like this machine learning ops Slack this morning, and someone made this meme, which I kind of liked. Yeah, monitoring KL divergence is worthless. Next, like commonly referred to metric is the KS statistic, which is like the statistic that goes into the KS test in stats that you might be familiar with. This is how it's defined mathematically, but like the way to interpret this is that this is like the maximum distance between the CDFs of the two different distributions. I just described the interpretation to you, so you know that it's like quite easy to interpret. You can like plot on a chart what this refers to, and it's used quite widely in practice. So this is something that I would recommend using. Just say yes to KS. And caveat here is this is referring to the KS statistic itself, not necessarily the statistical test where you actually get a p-value back from it. And I'll come back to that in a second. It's like the statistic that goes into the test that produces the p-value. Next distance metric is one that you might not be familiar with because it's not too widely used outside of this particular use case. It's a D1 distance, and this is the way it's described. It's the sum of differences between the values in the PDFs. Yeah, that should be sum of distances between the PDFs, not the CDFs. And the reason why this is worth bringing up is because this is the distance metric that, like after spending much time thinking about this at Google, is the one that they use in their systems. My caveat with this is always, isn't this a little bit hacky? Are you just like summing up the differences between the probability density functions? Like, why is that a meaningful distance? What's the justification for this? I don't really know. But it's really easy to interpret. This is what the interpretation looks like. And if Google does it, maybe it's not all that bad. So I think this is another good distance metric to look at for monitoring distribution change. There's many other distance metrics that you might be familiar with or you might see if you read about this subject. Earth mover distance is like a pretty cool one. Talk about the Earth mover distance, it's pretty cool. It's population stability index, lots of other stuff. I think like many of these distance metrics could be really good for your use case or even just for monitoring in general. And so I'd say it's like worthy of some research, worthy of trying out other distance metrics that you're excited about. And I think that there's like some missing research here. In fact, like a request for research here is I would love to see a study that looks at different types of drift from the perspective of how those affect the performance of trained machine learning models. So if you have drifts that are measured by these different metrics, do those have different impacts on the machine learning models that are trained on that data? All right, so that's the one-dimensional case. We have some distance metrics that we can use there. Next, let's talk about what you do when you're working with higher dimensional data. First caveat here is this is very much an open problem. I don't think there is a good solution to this yet. Some things you can try are you can use an explicit like multi-dimensional test like the maximum mean discrepancy. The way to understand this at a high level is you're looking at the distance between the means of the distributions in some embedded space. So that's one thing that's worth trying. Another thing that's really common to do in practice is just do a bunch of one-dimensional comparisons and look at all the distance metrics for all the different features and take, let's say, the max of those. So there's some things that are not very nice about that. It doesn't capture cross-correlation between the features, and you run into the multiple hypothesis testing problem, but this is a thing that people often do. Rather than looking at do the comparisons for all of your features, you might also like prioritize some of the features. So you might use some of like maybe the interpretability methods that we talked about last week, like feature importance, and just say, okay, we're only going to measure drift along the like 10 most important features. And then the last like kind of category of techniques that I'll mention here is called projections. And so projections are basically what they sound like. I think as far as I can tell, they were proposed for machine learning model monitoring in this paper called Failing Loudly, which is one of the only, like, strangely, like one of the only main track machine learning conference papers on data set drift that I've been able to find. And the approach that they advocate for is you first take your raw data, let's say your image, you pass that through some black box dimensionality reduction technique. It can be a random projection, it can be an autoencoder that's pre-trained, an autoencoder that's randomly initialized, or some other options. That projects the thing down to a lower dimensional space. So instead of an image, maybe you have a 32-dimensional vector or something like that. And then you run a 2-sample statistical test on that lower dimensional data. So you can aggregate any of the one-dimensional tests that we talked about before, or you can run a maximum mean discrepancy test. And in their experiments, I think they found it didn't really matter too much which one you did. So there's different ways that you can project the data. In their paper, they used things like random projections, randomly initialized autoencoders, pre-trained autoencoders, stuff like that. But you could also, like, one thing that I think is like a good idea to do in practice if you have high dimensional data is to use projections that come from your domain specific knowledge. For example, like if you're monitoring images, you might want to like project that image down to the mean pixel value and monitor that. And if that pixel value gets too crazy, you might know that there's something weird going on with your distribution. In NLP, this might be like the length of the sentence, or it might be like some vocabulary, like what are the top 5 words, something like that. But you could also imagine defining any other sort of analytical projection that depends a lot on your domain and what you think could be important like features of that domain to monitor. And you can define that any way you want to. Another category of things here is random projections. So you can just like linearly project the data. This can work really well. Or statistical projections, training an autoencoder or another kind of density model, right? Like you might fit like a likelihood-based model to your data and then take the output of that model, like the likelihood of that data point, and monitor that. Or you might use like PCA or t-SNE or something like that to project the data and monitor the result of that. Yeah, and so I think the last thing I would say on like measuring the distance between these distributions is that like when you think about it from a higher level, what do we really want to be measuring here? The thing that you want to measure is the reason why we care about measuring drifts is because we don't necessarily have access to the ground truth performance of the model. If you had access to the ground truth performance of the model, that would tell you what you need to know about drift, which is my model getting worse? And so really, I think what in a perfect world, the way that these techniques would work is that rather than giving you like some kind of abstract drift score, which can be hard to interpret, and you don't really know like whether a drift of a certain amount really affects your model performance, or if it affects your model performance, whether that performance change is material. I think the direction that techniques in the space should go is toward techniques that give you actually some approximate performance of the model on that data. So techniques that combine both some of these statistical ways of telling whether the data looks different, and then also some sensitivity that is specific to your model that tells you like whether drift of a certain amount, like how much you might expect that to alter your model performance. And so I only mention that because I think that this is like the direction that the field should go. And so if any of you are like interested in doing some research, I think there's like some interesting research to be done there, but I don't think that you'll find too much in the literature about that. And it's typically not how people do it in practice now. All right, moving on. So we talked about what things you should be monitoring, how you should be measuring changes. And then the next question, which I alluded to earlier, is like, how do you actually tell if that change is bad? Like, how do you know if you should do something about the change? Fortunately, again, this is another place where there's not a very satisfying answer. So I think there's one approach that you can take here to setting thresholds on test values, which is using statistical tests. So the kind of like canonical example here would be using the KS test as opposed to the KS statistic. So the KS test is a way of getting like a p-value for whether these two distributions are the same, like whether these two samples of data came from the same distribution or not. And unfortunately, this is like the wrong thing to measure for detecting data drift, because when you have a lot of data, then like any kind of minor change in the distribution, even if it's one that's like completely insignificant, is going to give you tiny p-values, right? Because even if the mean of your distribution is just shifted by a tiny amount, like if you have enough data, then the statistical test will tell you, oh yeah, p equals 0, these are different distributions. And that's not really what we care about in machine learning monitoring, because generally your models will be robust to small shifts like that. So those p-values don't end up being very useful in practice. There's a number of other ways of setting these thresholds, like these from this blog post from this like data quality company called Anomalo. So you can set fixed rules, never have any null values. You can have ranges. Okay, this test should always be between these values, and set that manually. You can look at the time series of the values of the test and like actually run that through an outlier detection model and fire an alert whenever it looks like an outlier. Or you could even imagine like training an unsupervised learning model on the values of that test and then using that to determine whether something is like an acceptable value or not. In practice, you'll almost always see these two techniques used. Unfortunately, at this point, it still generally comes down to a human being looking at this and setting the rule themselves for what they think an acceptable amount of change in the distribution might be. But I think the latter categories might be interesting areas for research. Although I hope it gets combined with model performance like I described earlier. Oh yeah, I forgot I had a slide on this, but yeah, I'll reiterate my request for research for approximating how model performance changes given a change in data distribution. All right, next, quickly just give you an overview of some of the tools that are out there to help with this. So there's system monitoring tools. These are useful for like setting alerts for when things go wrong, and cloud providers have like decent monitoring solutions where you can just pipe your data and your metrics into them. They'll help you set alerts for them. Anything that you can log in there can be monitored, and we may take a look at this in lab, but we may actually change up the lab as well. So some examples are, you have your cloud provider tools like Amazon CloudWatch, and then there's like specific tools that have evolved just to solve this problem. New Relic, Datadog, Honeycomb are some of the more prominent examples. Next category of tools that's worth knowing about is data quality tools. And so these tools are really aimed at like answering some of these data quality questions. So for a fixed window of data, can you tell me if this violates any of these handwritten or like machine learned rules about whether the data looks really different relative to the rules I've set? So Great Expectations, I mentioned earlier, is a pretty popular up and coming open source library for this. And then there's a few vendors that provide solutions for this, Monte Carlo and Anomalo being two of the ones that I hear discussed the most. And then lastly, there's a category of tools that's emerging around machine learning monitoring. Arise, Arthur, and Fiddler sort of being the best known examples. I think too early to say to have a recommendation here yet, but keep an eye on this space. I think there's going to be a lot of interesting stuff that comes out around it. So that was like the very lightning overview of tools. Last kind of topic on monitoring I want to cover is putting monitoring in the context of your broader machine learning system. So I think when people think of monitoring in a traditional software system, they see it as this thing where it's like useful for helping you catch bugs and catching when things go wrong in production. But those bugs are usually like pretty loud failures. They're like exceptions or events like that are relatively easy to detect on their own. And the data that you put into a monitoring system in a traditional machine learning system is things like system metrics, CPU utilization, request latency, things like that. And I think in the traditional software world, you think of these things as like data that's primarily useful just to like detect and diagnose problems with your system. So if your system is performing well, fundamentally you don't really care that much about what the request latency was a month ago or what the distribution of request latencies was. It's like data that you only really need when something's going wrong. In machine learning, I think like monitoring is in some sense much more central to the entire process of building and iterating on machine learning models than it is in traditional software. The two main reasons for this. One is that, unlike in traditional software, in machine learning, normally when you have a bug, what that bug leads to is just a silent degradation in performance. And so these bugs can be like extremely difficult to catch because they have very little signature. And on top of that, the data that we're talking about monitoring here, not system metrics, like things like model inputs, is like quite literally the code that you're going to use to produce the next version of your model, right? Like the data that goes into the model, the predictions that come out, the labels, that's your training data for when you retrain your model. So in some sense, it feels like this system has to be more important to the model building and maintenance process. People typically think of monitoring, I think where you see it fitting into like your system diagram is let's say in a machine learning system, you train a model, you evaluate it, you put it into production, and then monitoring is this like module that you slap on top of that. And your monitoring thing is like, watching your production system and helping you find out when things go awry in that production system. But I think the reality of monitoring and machine learning is that your monitoring system really actually needs to be pretty tightly integrated with the rest of your production stack. I'll talk about like ways in which I think it should be integrated in a second. But because of this, I've started using a different name to describe what this system actually is, which I've been calling an evaluation store. Just as a way of distinguishing this in people's minds from, okay, this is just a module that we slap on top. This is something that really needs to talk to the rest of your machine learning system. And in particular, I think one of the roles that a monitoring system could play in your machine learning infrastructure is helping you close the data flywheel. Right? So the data flywheel is a concept that we've talked to you about before, where as you get more and more data, you use that data to train better models, makes your product better. Better product gets you more users, get you more data, and more data allows you to close the loop and make the model better over time. And so let's talk about how this monitoring system or this evaluation store could help close the data flywheel. So at training time, and so the one distinction I'll make here is that I think I mentioned this, I think, in the testing lecture too, but I think when you think about your monitoring system, if my kind of hypothesis is right, which is that in the longer term, the best way to monitor your models is going to be to have some way of using the data that's coming in to approximate how performance might have changed on your model on that data, then if that's the case, then your monitoring system needs to be integrated with your training and evaluation system as well, because training and evaluation is where you'll build those models of the mapping between data change and model performance. And so I've started thinking of your kind of monitoring system or your evaluation store as a sort of cohesive evaluation system that is used not only for monitoring per se, but also for offline evaluation. And so the ways that this would interact with the rest of your stack are when you're training your model, you want to register your data distribution and your model performance into the system so that you have something to compare to when you're in production. But evaluation store or your monitoring system could also help you catch performance bugs or implementation bugs during training. For example, if you made a bug in how you're training your model and all of a sudden your training data looks nothing like your production data, that might be something you want to catch earlier rather than later. When you're testing your model, you might want to actually record that data here as well. In deployment, we've talked a little bit about running things like A/B tests. If you have a centralized system for keeping track of model performance metrics, then that system is what you'll use to run an A/B test, because you'll just ask the system okay, how does the performance or maybe the approximate performance of my model of these two versions of my model differ on this slice of production data. Monitoring is a relatively straightforward application of this. You'll ask your monitoring system how well you think the model is performing in expectation. But I think where it starts to get interesting is when you talk about closing the loop. One challenge for a lot of companies when they're just deciding what data to collect from their machine learning system is that with really high data volumes, on a robot or on a web scale application or something, you can't necessarily store and label and train all of the data that's going through your model. So you need to pick a subset of that data to store, label, and train on. And so how do you pick that subset? The simplest thing that most people do is they'll just randomly subsample that data. But that can be I think probably not the most efficient thing. Because if you have tails of your distribution or areas where your model is not performing well, you might want to oversample data from those areas. And so another function that your monitoring system or your evaluation store could play is you might want to oversample data from regions that have low approximate performance. So if it looks like maybe your model's not doing too well on this data point or this window of data points, you might want to sample more data from that window. Cleaning and labeling, I think, is a similar story, right? You might want to label more data that has low approximate performance. And then retraining, right? Another kind of challenging problem to figure out is when should I retrain my model? How often should I retrain my model? Conceptually, the way to make that decision is the cost-benefit analysis, right? There's some cost that's associated with retraining your model, compute costs, data costs. And so you want to be able to measure what's the approximate benefit of retraining my model? How much better could my model get by retraining it? And so one proxy for that might be knowing how much you think your model has degraded in performance relative to the last time that you trained that. And so this system, this monitoring or evaluation store system, could help you answer this question of when you retrain. So takeaways on monitoring. I think if you're going to take one thing away from this, it's just do it. Monitor your models. It's a good idea. I think there's been a culture in the machine learning field for a long time of machine learning people, machine learning focused people, not necessarily caring too much what happens to their models after they get shipped. like thinking like, oh, it's my job is to produce the model, not to maintain it. I think one mindset that I hope that you all adopt as you go on to implement machine learning models in industry is that what happens to the model after you deploy it is still, at least in part, your responsibility, right? Because you're the one who built the model. You know what the data that it's trained on looks like. You know how to fix it when things go wrong. And so monitoring is something that you should be thinking about because something will go wrong. Like models, I think it would be very unusual to have a model that you can just put in production and leave there and have it never break. And so you should at least have systems in place to know if something is going wrong. If you're getting started on monitoring, I think the kind of like pragmatic starting point is by looking at these data quality metrics. So these rules about, okay, are all my features within some allowable range? Are all of the means of my features within an allowable range as well? And looking at system metrics. And main reason that those are the recommendations are because they're the easiest and they'll already start to catch a lot of bugs for you. In a perfect world, I think the role that your monitoring system should come to play in your machine learning system is that it should be fused with your testing system. And it, like the bigger, like the sort of higher order calling it should have is not just helping you tell when things go wrong in a sort of abstract way, but helping you like close the data flywheel and fix your system and train on better data over time. Because these same approximate performance metrics that you're using your monitoring system to estimate are the same metrics that you should be using to decide what data to collect, label, and retrain on. And then another note here is like the tooling here is not really that mature yet, but this is a pretty active space for like startups and other companies. So it's one to keep an eye on. And I think that in spite of all this, there's a number of, I think this is like a very under-researched area. It's a super important problem for making machine learning systems work in the real world. And there's like a painful lack of research on how to make this work well. And so there's big open research questions here. And if you're like looking for stuff to do research on, I would highly encourage checking it out. All right, that's all I have for today. Thank you.